In this module, we will be learning about Lorentz force. As you learned earlier, charges at rest produce an electric field. Moving charges or a current passing through a conductor produces both an electric and a magnetic field around it. A magnetic field is a vector quantity. It is denoted as B when we represent it vectorially. The properties of a magnetic field are identical to those of an electric field. Similar to an electric field, the magnetic field also obeys the principle of superposition. Consider B1, B2, and B3 as magnetic fields at a point shown due to three different sources, such as three current-carrying conductors. Then, the resultant magnetic field B at the point is the vector sum of the individual magnetic fields. That is, B is equal to B1 plus B2 plus B3. Now, let us learn about the forces acting on a moving charge in the presence of both an electric field and a magnetic field, which is called Lorentz force. Consider a charge of Q coulomb placed in uniform electric field of strength E. Here, the force acting on the charge due to the electrical field is F electric is equal to QE. Consider another charge of Q coulomb moving with the velocity of V in the magnetic field B. Here, the force acting on the moving charge due to the magnetic field is F magnetic is equal to Q into V cross B. The force F is perpendicular to the plane containing the velocity vector and the magnetic field vector. Now, consider a charge of Q coulomb moving with the velocity V in the presence of both electric fields E and the magnetic field B. The net force on charge Q is F, called Lorentz force, and is acting on the charge and is equal to the vector sum of the forces due to the electric field and magnetic fields. Thus, Lorentz force F is equal to F electric plus F magnetic. That is, F is equal to QE plus Q into V cross B, which can be written as F is equal to Q into E plus V cross B. Now, let us discuss in detail the interaction of a moving charge with the magnetic field. As you know, the force experienced by a moving charge due to the magnetic field is F magnetic is equal to Q into V cross B. As V cross B is equal to VB sine theta, the magnetic force on charge F magnetic is equal to QVB sine theta, where the angle between the directions of V and B is equal to theta. When theta is 0 degrees or 180 degrees, that is, when charged Q moves parallel or anti-parallel, respectively, to the magnetic field, we have sine theta is equal to 0. If the charge is moving perpendicular to the direction of magnetic field, theta is equal to 90 degrees. In this case, the charge experiences maximum magnetic force, F magnetic equal to QVB. If the charge is not moving in the magnetic field, that is, its velocity is 0, then the charge does not experience any force, since F magnetic is equal to 0. When the charge in the magnetic field experiences maximum force, the force is expressed as magnetic force is equal to BQV, which can be written as B is equal to F by QV. The magnetic field strength B can be defined as force per unit charge when the charge is moving perpendicular to the magnetic field with the velocity of 1 meter per second. The SI unit of magnetic field is Newton per ampere meter, which is referred to as Tesla. Gauss is another common unit. 1 Tesla is equal to 1 Newton per ampere meter. 1 Tesla is also equal to 10 to the power 4 Gauss. Now, let us discuss magnetic force acting on a current-carrying conductor. Consider a conductor of length L with uniform cross-section A and the number of free electrons per unit volume as N. These electrons are moving with an average drift velocity v. Then, the total number of free electrons in the rod is equal to N times the volume of the rod, which is equal to N into Al. The total charge on the rod is equal to the total number of electrons multiplied by the charge on an electron. That is, Q is equal to NaL multiplied by minus E, where minus E is the charge on an electron. This conducting rod is placed in a magnetic field of strength B. As you learned earlier, for a charge of Q coulomb moving with a velocity v, in the magnetic field B, the force acting on the moving charge due to the magnetic field is F magnetic is equal to Q into V cross B. In the case of the rod, the magnetic force acting on the free electrons is equal to the total charge due to the free electrons on the rod multiplied by V cross B, which is equal to minus NaLe into V cross B. As current density J is defined as the current per unit area, it is equal to current I divided by area A, which is equal to minus NeV, where minus E is the charge on the electron and V is the average drift velocity. In this case, the magnetic force can be written as F is equal to Al multiplied by J cross B, since J is equal to minus NeV. From the definition of current density, current I is equal to J multiplied by A. Then the magnetic force F is equal to I multiplied by L cross B, which can be written as F is equal to BIL sin theta.